Howdy, students. We're going to do something a little bit different today. We're going to take the thinking of a very well known, high profile, highly recognized and celebrated futurist, a positive futurist, we could say, in that he was sometimes called a utopian, and he wrote a book called Utopia or Oblivion, so he didn't totally discourage being called a utopian either. But we're not going to get into his utopian futurism. We're going to get into his geometry, which is also a philosophy. And, there's a lot of that. There's the whole theosophy library. There's a vast amount of sort of mystical geometries out there. And so you could say, okay, so he's one more of those kind of architects who on the side has kind of a hobby in geometry and has come up with some interesting jargon, some nomenclature like particles, and he's got these things called modules, same as particles. And he means that in a very generic sense, as in container. So synergetics being a geometry, his geometry, is about containers, things inside other things, but also in time, so they come and go. So there's before and after. So there's energy involved. Like I say, it's a philosophy. It doesn't confine itself to only geometric concerns, right? So there's a picture of the volumes. I've got critical path in between the two volumes. You see synergetics and synergetics 2. These come out in like the 70s, mid to late 70s. And then in the 80s, we get Critical Path, and there's also Grunch of Giants, Tetra Scroll, lots of books that he wrote and have been written about him. So he's a very researchable guy. So if you get interested in, say, this math and you want to know more about the person, there's a lot. And so I'm just not going to go through it all here, obviously, but I just wanted to put a suggestive slide or two. He was very tied in with the military-industrial complex in a way, but like I said, he's a positive futurist. So he wanted the ideologies to compete at the level of who can offer the best living standard, for example, not who has the most awesome weapons or whatever. And his work was adapted for use during the Cold War to do these radomes, which shelter internal expensive electronics that shouldn't get wet, radars and stuff, or get blown around too much. So these are very sturdy structures. Now you're going to get totally lost trying to follow any of the synergetic stuff if you're not familiar with the idea of a unit volume tetrahedron. It still has rational edges as well. Like we're talking about a tetrahedron with edges 1 and yet volume 1. And we don't have that in sort of Greek metaphysics, Western civilization, whatever you want to call it. It's a fork in the road that hadn't been taken. And so I think Fuller jumps from being a hobbyist to an innovator in the math world by taking this step. You can see there is a ratio. In other words, if we take the unit cube to have edges r, and if we take the unit tetrahedron to have edges d, where d is the diameter of a ball and r is the radius, so d is simply twice r. So we have these two geometric figures side by side, and either one can be our unit of volume. Now, if you do that, there's a consistent way to tackle volume in general. It's a logically coherent paradigm. And there at the bottom center, you see the focus of this talk, which is the beast modules. And we say right out of the gate, these are volume relationships that we're talking about. And A, B, and T have the same volume, 1/24th. And then the T is less than the E, and the E is less than the S in terms of, their size. And there you go, a little sort of crib sheet as to what those values would be if we define phi or phi, I say phi, as the golden mean, right? Square root of 5 plus 1 all over 2. Then the A, B, and T modules I'm talking about at the bottom center of the slide all have volume 1/24th. And then the S module is 1 over 2 phi to the fifth. And the E module is second root of 2 over 8 phi to the third, right? So those are denominator phi's. And you start to see a chart starts coming into view as we can assemble or express our normal everyday polyhedrons in terms of their tetrahedral volumes, unit volume tetrahedron, including these modules down here. Those are all tetravolume values. In the chart at the top, all the volumetric expressions on the right side, they'll be unfamiliar. And also how we do coordinates, XYZ versus IVM coordinates. It incorporates the volume computation changes in sort of one alternative approach, which is very familiar, however. It feels like you're using XYZ vectors. The concepts all translate easily, so once you know high school math a little bit, like XYZ, going to IVM is not a big deal. And yes, those are determinants of matrices. This is if we start using quadratic coordinates and we want to directly compute the volume of any tetrahedron defined by 4 vertices, whether expressed in quadratic coordinates or in terms of the lengths of the 6 edges, right? A, B, C, D, E, F, 6 edges. So this is the kind of stuff we get into in synergetics. You're probably surprised. Why is this not even mentioned usually? Like, why do I go through all of high school and this kind of high school never happens? Like, I never learned that the most credentialed, celebrated positive futurist in American history came up with some interesting geometry focused around 5 modules that he named the A and the B, the T and the E, and the S. So here are the A's. You see there's a reference to his great pirate. There's a lot of little allusions here in these slides to other parts in the literature. And there are a lot of excerpts directly from synergetics itself, such as these 2 grayscale pictures, embellished with Python around the edges, because we do a lot with Python in this curriculum as well. So going back to the 60s, when Fuller was teaching, had his World Game workshops and so forth, there was a lot of buzz about this upcoming synergetics that hadn't been published yet. And Robert Williams got to see an early copy of synergetics pre-publication and picked up on the A and the B particles that Fuller was starting to define. But he defined his B particle in a way that it was twice as big as the A. It wasn't like they both had volume the same. And he hadn't picked up on the whole tetravolume thing very much. So I'm just saying the evidence of this nomenclature coming over the horizon puts it back to the 60s, but then synergetics itself doesn't get published until the 70s. And so here we're looking at a combination of later graphics by students of Fuller and Fuller's graphics in synergetics, such as on the right. The A and the B modules there are depicted in terms of a regular tetrahedron. You can see the same depiction in the upper left. And then, you could go on and say, oh, and then so there's a C module and a D module, and they all have the same volume, E, F, G, H, and so on, as predicted here. That's a whole discussion, why they have the same volume, what can you distort here to keep the volume. And no, we don't actually use C, D, E, F, G anywhere else, really. It's just partly to give you this idea of a progression, and then we abandon needing those letters for those things, because the E module is going to be something else entirely when we get to it, which is shortly. So you see how the B sits on top of the A there in the octahedron in the upper left, the yellow. B module has the same volume, though, as the A module, which is in light blue. And so with these, we assemble and or express the volume of various other polyhedra. This is where, we get into the whole idea of plane nets. So this being, say high school geometry, we want plane nets anyway. We want to fold up these tetrahedrons from these little flat sort of origami guides, kind of in a way. So then we want to know the exact, relationships between those edges. We want to know the exact ratios here. So we're doing just your basic computational geometry, but we're quickly getting into volumetric geometry and talking about space filling. It's pretty esoteric math to talk about which tetrahedra fill space without chirality, without left and right. And the mite is one of them, and the mite is shown here, made of two A's. There is a left and a right A, and then either a left or a right B. Either way, you get a mite, but then the mite itself has no chirality. And here we're using mites. There's a toy with magnetized mites that you can get that lets you build, say, a cube. Clearly, if you can build a cube with all mites and the cube itself's a space filler without gaps, by space filling I mean it like bricks together to leave no gaps and to fill space in all directions. That's like cubes do that, and since mites make cubes, clearly mites do that too, but so do some other polyhedra, irregular polyhedra. Regular tetrahedra don't fill space. So that whole discussion is part of this. And again, it crisscrosses other math that's going on at the same time, the 1900s. Fuller was not necessarily able to keep up on all the research going on around him either, so it's still up to us to stitch it together looking back, see how he was on the same page, was not on the same page. Where he wasn't really on the same page is he didn't use Greek letter phi or phi to stand for this quantity, square root of 5 plus 1 over 2, all over 2. But if you do that, if you bring that back, which is something we've been doing in the synergetics community, you get a lot of simplification, a lot of cool sort of shortcut notations in a way, as you've seen so far, as I've used phi quite a bit already. And this is a reminder. Now, what is this toy that I'm using? This looks like plastic rods are those magnets that you screw in and then have metal balls? I'll show you another picture of that toy in a second. But here's the volumes table that we're starting to build up. And we're going to have, a whole number of volumes that we're not used to from everyday math. We don't even get to polyhedrons much in current high school. They're in the back of the 10th grade geometry book, maybe. We studied geometry in 10th grade. We don't really get to the back of the book. There's too much to know. Again, these are all in tetravolumes. So this is like double removed from anything. This is not what high school's like, nor is this what college is like. There's that toy again. And yes, it is kind of screw-in, high-power magnet cones gripping these ball bearings. A toy that I did these graphics for. This is one of my renderings. It's not a photograph, and the toy itself did not make it to market. So the T and the E modules in synergetics are going to be derived from the rhombic triicontohedron shown here, a 30 diamond face polyhedron that's just hugging and just tangent to one of the IVM or sort of unit radius balls that we're going to be using to make our sphere packing lattice, right? That's part of synergetics as well. And you're going to say, well, that's part of everyday crystallography. I mean, it's not like, what? Are you saying Fuller invented the, cubic close packing or the FCC? Isn't that why Fuller's been discredited? Because he claimed credit for things that everybody knows? And that's the spin on the story from people who want to discredit the guy. But of course, he well knew that this was a focus in the literature, the octahedron, tetrahedron honeycomb. He didn't know that Alexander Graham Bell was into it necessarily, but found out. But he did hold a patent on what he called the octet truss. So he did use this lattice in a technological way that was, unique enough to get into the patent law. And this is how he documented his work as opposed to getting published math papers. he would get things patented. And that kind of went to his claim that if you commit your life to serving all humans, you become a genius, basically. That's what he thought. And so he became very productive because he had committed his life in 1927 to let's stop playing these like me or you games and do like all for one and one for all kind of stuff. And he did feel at that point going forward that his IQ just kept going up and up. It's kind of like that movie Lucy with Sarah Johansson. Okay, except she's more better looking character, and probably that's a more exciting movie, so you could watch that. But think about Fuller getting smarter with age and coming up with all these interesting modules with which to express volume as we normally do anyway. We're always expressing volume, but always in cubes. What an interesting thing to take tetrahedrons and use them instead. So the E and the T are two of these modules. We've talked about their volume already, but they're very similar in their volume. In terms of decimal points, they're just a little bit different, but their different role is that the E module is rhombic tricondahedron, 120 of them completely enwrap or contain an IVM ball, whereas the T modules, RT, rhombic tricondahedron, its claim to fame is its volume is exactly 5. And once you've got a 5-sized RT, just blow it up by 3 halves, meaning, multiply the edges such that the volume goes up to 7.5, and you've got this red RT that just shares vertices with the synergetics cube of volume 3, the octahedron volume 4, and so forth. So that's why it says RT scaled up by 3 halves on the left, and then you are adjoining this world where the outermost cube is the volume 24 cube. But the inner cube that we're touching its vertices, sharing vertices with, that's the volume 3 cube. Casey House doing some excellent posters on our last featured module here. Again, phi becomes important. It's the shortcut, and that is the S module here shown in synergetics. Here is shown as bricking in the empty space between a icosahedron inside of an octahedron. And that's not just any octahedron, that's our volume 4 regular octahedron, inside of which is a faces flush icosahedron of 20 triangular faces, all the same equilateral triangles, and then that leaves a gap to be filled in by 24 S modules. And once again, we compute all of the edges. They're given to us in synergetics. You can also just, make it a whole project to figure out what those edges have to be. Learn a lot of geometry and then apply it immediately to these kinds of questions, construction questions. And then write Python. This is a great way to learn, right? I'm defining an S module as a subclass of tetrahedron here on the left. I'm giving the edges according to certain ordering that's predefined, and I'm creating a tetrahedron right out of the bag. That is the S module, and here we're doing that again on the right side. You can see how in input 271, I'm creating my S tetrahedron. I'm outputting the volume without evaluation, so just running it through our volume formula, but when I actually turn it into a decimal, it's 0.0450849718747 and so forth. So that's the volume of the S module. I can also list out its edges in algebraic expressions. And once we have this interesting relationship of the S modules, we can expand them. We can scale them up by phi and down by 1 over phi. So we get these interesting relationships, here we're doing that, where we can express our regular volumes in terms of phi scaled S and E modules. So the regular S module is phi to the negative 5 over 2. And if we scale that up, that means multiply all of its edges by phi. That's equivalent to increasing the volume by phi to the third power, because volume goes up as a third power of the scale factor applied to each edge. So if you double all the edges, volume goes up by a factor of 8. If you halve all the edges, volume goes down by a factor of 1/8. And so we apply that to the S module to get what we call S3, S6, S9, and so on. And that's scaling up by phi every time. Volume goes up by phi to the third. Or we go down by using 1 over phi as our scale factor applied to each edge. The entire volume goes down by phi to the -3, or 1 over phi to the third, and so forth. That ratchets us down to S lowercase s6, lowercase s9, meaning we're going down in size or up in size. You can 3D print these S modules and pour liquid back and forth and stuff. Here on the right, though, you'll see that once you've got your S module, if you scale it up to the S6 and scale it up less to the S3 and just add them together, you get a volume of 1. And it just works out algebraically as we're showing here, and so that's why we can get by with what we call these Koski identities showing now on the screen, where you can take the whole number of volumes we already had for, say, tetrahedron, cube, octahedron, and so forth, and re-express them if you would like to in terms of phi-scaled S and E modules according to this table. I would call this interesting mnemonics. It's like it all hangs together tightly. Everything references back to itself. It's a very satisfying mental geometry that gives you tons of information, lots to practice with, and it all fits into, like you could say, a tightly wadded little ball of interconnected concepts. Same idea here. There's your concentric hierarchy at the top and your volumes table underneath. And you'll see these whole number volumes, which are just zeros all the way across, like the rhombic dodecahedron. They're color coordinated with other literature that you will find throughout the School of Tomorrow. So this was our lecture on synergetics, the hardcore, we could call it, which are the 5 beast modules. And now that you have a grasp of what's at the core of synergetics, you actually have advanced into the 0.1% of Americans who have any clue that there is A, synergetics, and B, it was written by a great futurist. He promised a lot, not in terms of I will deliver, but in terms of what our potential was. And it was really looked up to by a lot of people outside the U.S., you know. So to not follow, to not even teach any synergetics in the high schools, that was sending a very strong message in terms of foreign policy and so on. The math teacher's decision to not teach any of this stuff has determined a lot of the track that we have followed instead. So math teachers of the world, you guys are powerful. All right, so that's our slides, and feel free to use this deck and do more research. Don't take my word for anything, and go off and see how you want to spin it. Okay, talk to you later.